Today we will discuss the concepts of a polygon filling algorithm, which is termed in some literature as PolyFill or polygon filling, and it is based on a method of Scanline based drawing algorithm, where the polygon is filled based on scan lines from the top to the bottom. So, we will see the methodology behind polyfill or scan conversion of a polygon, as the concept is called. Okay. So, let us see a simple example of a polygon on a raster frame buffer or on a screen, and see what is the problem okay, when you need to fill the polygon, say with a particular color in this case, or a particular shade. Okay. Here we see an example of polygon filling with a polygon of 4 vertices or a quadrilateral. Okay. So, there are 4 vertices forming this polygon or a quadrilateral, and you can see that the region inside this polygon is filled with a different shade than the background color. The background I have chosen to be white color, and the color to be filled inside is filled with red. You can see the effect of aliasing of the pixels which are at the center of the grid. They are not the grid intersection points, but they are square pixels at the center of the grid, and you can see the effect of aliasing as for non-horizontal lines in this case. So, basically you can see here that the polygon filling is a case of filling horizontal lines from left to right, and you will have the effect of aliasing as you had for drawing straight lines using Bresenham's algorithm. Well, this is a slightly different arrangement of this polygon, where we consider now that the pixels may be at the intersection of the grids rather than or grid intersection points are the pixels rather than the center of a square. As you can see, if I define the polygon vertices as the with integer coordinate values which lie on the intersection points, it is possible that when you consider the intersection of a horizontal scan line, the scan line is a horizontal line with one of the edges of a polygon, the 2 vertical inclined edges, and you find that the intersection point is basically a floating point number, but we should not worry about this case, because we already know from line drawing algorithm to select the nearest integer. Okay. So, we know that we can actually draw a line with pixels which are the closest to a line or a straight line, and well, just find out which are the closest and which are integer values, and we can make, and we have also seen how an integer based algorithm can be used for drawing circles and ellipses. Almost a similar concept is used here, but we must ensure I must mention and specify here that we are not drawing lines. Okay. We are basically filling regions within a polygon, but that concept of integer based algorithm will also be used indirectly here. Okay. So, I must mention here with respect to this figure that although these the intersection points with the inclined edges of the polygon and the horizontal scan lines could be floating point numbers, all right, but you have to actually select the nearest integer coordinates or pixels which are at this at the intersection of the grid lines, and shade them. Okay. Change the color, and of course, all intersection points or pixels within this polygon must also be shaded. So, this is a clearer picture which illustrates or shows you how the polygon will appear after it is shading. So, this is the definition of the problem of what we are going to do, and let us assume to start with that the input to the problem in terms of an algorithm is that the following input is provided to the algorithm, that we have a set of integer coordinates which are the vertices of the polygon. Okay. So, we have vertices 1, vertex 2, vertex 3, vertex 4, and so on. There could be n different vertices, and our job is to find out the pixels which lie inside the polygon and also on the perimeter of the polygon. So, okay. So, that is a scan conversion. Why the name scan conversion is used, or what is called as a Scanline PolyFill algorithm? We will look at a very conceptual framework or steps of the algorithm which is used to implement, and then analyze these steps one by one and see with the help of algorithms how each step is implemented. Okay. We will have to get into concepts of graphics as well as mathematics to find out how this works. Okay. The first thing is, when a polygon is defined, you need to find the minimum enclosed rectangle. This minimum enclosed rectangle is a minimum rectangle which binds a polygon. Okay. So, when you have a polygon defined with a set of vertices 1, 2, 3, 4 up to n, and of course, the last line connects the nth vertex to the first vertex, or from a CS literature you can say vertex 0, 1, 2 and so on up to n minus 1. We are talking of n different vertices defined on a polygon. Well, we have to bother about a certain set of pixels which lie inside or around these vertices. So, basically we can concentrate to do a scan conversion on a minimum area which is defined by minimum enclosed rectangle, which is say a bounding box within which the polygon lies. Okay. So, you define a polygon and you find the minimum enclosed rectangle. That is a very simple problem as far as geometry is concerned, because what you have to do basically is find out from the list of x and y coordinates the minimum and the maximum value, that is x min and x max from the x coordinates. Where are the x coordinates? These are the coordinates of the vertices of the polygon. So, take the x coordinates of the vertices of the polygon, find out the x min and x max, which is the minimum and the maximum value, correct, and also take the sequence of y values, y coordinates of the vertices of the polygon, find the minimum and maximum value, that gives you y min and y max. So, x min x max and y min y max will give you the minimum enclosed rectangle. That is the minimum enclosed rectangle, the terminology means that is the rectangle with the minimal area which covers the entire polygon. Whatever shape the polygon may be, you cannot probably find a rectangle smaller than that which just fits it. Of course, you can take a larger rectangle, but then you have to work hard at the time spent will be more. So, we are looking into a smallest space which you have to analyze to find out which are the pixels you need to shade and which you do not. So, the first step involves conceptually, as we see here, find the minimum enclosed rectangle. So, that is the description of the first step, where you find x min, x max, y min, y max, and that gives you the minimum enclosed rectangle. From the y coordinates, maximum and minimum y coordinates of the minimum enclosed rectangle, you can find the number of scan lines you need to draw, that is the number of horizontal lines. I did say that you have a minimum enclosed rectangle, correct. You have a x min to x max, y min to y max as talked about, and from y min to y max, using the separation between the minimum y coordinates and the maximum y coordinates, you can find the exact number of scan lines or horizontal rows of pixels which you have to analyze to find out if some pixel is inside the polygon or outside the polygon, and then paint it or give it a color. So, the number of scan lines means the number of rows of pixels which start from the lowest row of the minimum enclosed rectangle to the topmost row of the minimum enclosed rectangle. So, the y max and y min difference plus 1 of course, because it is an integer we are talking about, the difference number of lines including the top one and the bottom one. So, you have to add 1 to that, will give you the number of scan lines from top to bottom or from bottom to top. Either way you can go, it does not matter, but you must be consistent that when you are moving either from top to bottom or from bottom to top. So, number of scan lines is given by the difference in the y coordinates of the minimum enclosed rectangle, y max minus y min plus 1. Okay. So, that these are the first two small steps. Then for each of these scan lines, how many number of scan lines you have to work on? This is given by the step number 2, that is y max minus y min plus 1. Okay. So, if y max is 10 and y min is 5, this number of scan lines will be 6. You can count yourself 5, 6, 7, 8, 9. Okay, and 10. So, that makes it 6 scan lines. Let us say with an example. So, for each scan lines, you have to do the following step. The first step is obtain intersection points of scan line with the polygon edges. We will see this with an example in the next slide. That means, our idea is to find out how many pixels within each scan line lie inside the polygon. So, what you can do is try to find out what are the edges which intersect with this particular scan line, and from those intersections you have to process them to find out which of these regions within the intersections are lying within the polygon or outside. You have to visualize an arbitrary polygon, not the simple polygon of a rectangle which we just talked about, are just shown in the slide before, 1 or 2 slides before. That's a very simple oversimplistic case, but you can assume something like a star type of a structure is an example of a very quite an arbitrary polygon. Okay? And if you take a scan line, what you will find is that there are some sections of the scan line which lie inside the polygon. We will take an example soon, and there are some sections which lie outside. This is again we are talking of a scan line within the minimum enclosed rectangle. If you take a scan line, some portions will be inside the area of the polygon, some will be outside. There are multiple such areas within a particular scan line which will be inside and some outside. So you have to find out which portions are inside or outside. But before doing that, which portion is before trying to find out or before finding out which regions or parts of the scan line are within the polygon and which are outside it, you must actually find out the intersection points of the scan line with the polygon edges. So that is the first step of this for loop, where we say for each scan line you obtain intersection points of scan line with polygon edges and then sort these intersections from left to right. Okay? So in ascending order from left to right in terms of x coordinates, you arrange these in ascending order, and let's see what do I and then you basically form pairs of intersections from this list. This is an example of a figure which I was talking about. This dashed brown line talks of a particular scan line within of course the rectangle, all right, and this is a polygon with 1, 2, 3, 4, 5, 6. Okay, so 6 vertices, and this is an example of an arbitrary scan line which intersects 4 different edges of the polygon, okay, which are marked by the circular blue large dots. Okay, so there are 4 intersections of these which you have to find first. That is the first step inside a for loop for this particular scan line only. And after you get these 4 intersection points, you have to arrange them in ascending order. You have to arrange them in ascending order from left to right in increasing x coordinate. So you will have x1, x2, x3 and x4, 4 different intersections, and then you form pairs. If you form, it is interesting property of this polygon, now you see, if you form pairs of intersection from this list, okay, that means you form a pair 1 and 2 and you form another pair 3, 4 and so on. If necessary, then you will find that you have to only fill up pairs, you have to fill up pixels within pairs. If you shift the scan line somewhere on the top, let us see here, you will actually obtain 1 pair of intersections. So the number of intersections of a polygon in general, the number of intersections of the edges of the polygon with a particular scan line, I repeat, is always an even number. That means that's why you can form pairs. I repeat again, you can try it with arbitrary shapes, except there are certain exceptions. We will talk about that very soon. Okay? In general, if you take a polygon and draw arbitrary scan lines, you will find that, you can try it in a piece of paper right now, that the number of intersections formed are in general even numbers, the number of intersections which you have. And since the number of intersections are even numbers, you can form pairs. Okay? As in this example we have seen, if you take a line as we have taken in this figure, there are 4 intersections. So you can form 2 pairs. If you shift the scan line to the top of the figure somewhere within the polygon, of course, you will get 2 intersections or 1 pair. Okay? So depending upon the nature of the polygon, the shape of the polygon, or even the size, you may have different number of intersections of the edges with the scan line. But in general, typically you will find that the number of intersections are even numbers, and if they are even numbers, you can form pairs. So that is what you see here, you form pairs of intersections from the list. There are exceptions which talk that if a scan line passes through a vertex, okay, then you might have a problem. That means intersections at vertices may require special handling, because the vertex is a combination of 2 different edges. So what do you do? Should you take both the edges as intersections, or which one should you take? So except the case when a scan line is passing through a vertex, which could be at the end here or somewhere at the middle, you may have a problem. As for example, if you take the top scan line, it will have basically 1 intersection at this vertex, but that you can easily visualize that that particular intersection is formed by 2 edges, and hence actually there are 2 intersections. So we will see later on how to handle vertices, because the vertices require special handling at the intersections. Otherwise, typically in general you will have pairs of intersection and you form pairs, because the number of intersections are even number. So, assuming that the number of intersections is an even number, you form pairs and fill within pairs. So, fill the pixels within the first pair, leave between the second and the third, take the second pair which is between third and fourth, fill in pixels in between, and next everything after 4 also you leave out. So, fill within pairs, as you can see for this particular scan line, or if you take somewhere in the top here, you will form one pair. So, fill means fill the pixels, equivalent to a draw pixel command, which we have seen earlier. In the case of a draw line, draw circle, we had a draw pixel command, x comma y, all those pixels which are within this pair, okay, or pairs is what you fill up. Intersection points are updated for each scan line, okay, that you have to do, and that is an advantage, because if we will use a concept which we will later on see as scanline coherence or edge coherence, where we will find that if you know the set of intersections for a particular scan line which intersects edges at certain points, you will find that for the next successive scan line, which is at say y plus 1 or y minus 1, the position of the intersection points do not change much. In fact, the next intersection point can be obtained by the concept of what we have seen as integer based algorithms of Bressenham's to find the next pixel for a line. So, updating intersection points is very easy. The concept is used here is exactly the similar as the Bressenham's line drawing algorithm, where you find the next pixel. Either you are moving from top to bottom or bottom to top, does not matter. You find the next pixel of intersection for each edge with respect to the next scan line by a simple update. Based on Bressenham's algorithm. And so, that is the point here which you are talking about, saying that intersection points are updated for each scan line, and you stop when a scan line has reached y max. So, you start from y min and stop at y max. Y min, if you say the bottom of the screen is 0, you start at the bottom and finish at the top, or vice versa. So, you basically start from the scan line y min and stop when the scan line has reached the maximum value at y max. So, I will roll it back once again, the conceptual steps of implementation for a Scanline PolyFill algorithm: find the minimum enclosed rectangle, find the number of scan line, and when you know what are the number of scan lines for each scan line, do the following steps. So, we have about 5 or 6 steps. The first step is obtain intersection points of scan line with polygon edges, sort intersections from left to right, form pairs of intersections from the list. Of course, intersections at vertices require special handling, we know that now, and then fill within pairs, and then the intersection points are updated for each scan line. So, these are the conceptual steps of implementation of a scan line, and you stop the scan line when you reach the scan line reaches y max. So, you start at y min, and of course, at each point you do not have to recalculate the intersection points again for a scan line. That is interesting. Okay. You can make the algorithm work faster using in concepts of Bressenham's algorithm of looking for the next east or northeast pixel based on integer algorithm, because basically intersection points are all lying on a line. So, if you know the pixels to if you know how to calculate the pixels on a line based on Bressenham's algorithm, and given a pixel picked up at the current point of iteration, you can always go to the next pixel by a simple update which we used for Bressenham's algorithm. So, that is what you need to do as an update rather than calculate afresh for the next scan line new set of intersections. No, you need to start at some point which are typically a vertex or a vertices, and then keep on updating them using the Bressenham's criteria, which makes the algorithm very fast. The only precaution, of course, there are quite a bit of precautions necessary. The first precaution which we will study now is how to take care of intersections at the vertices. The question is, now we will also first study why the particular point inside a scan line, if it is within a pair, should be shaded with a pixel, and if it is not within a pair, it should not be shaded. So, what is the check that if a point is within a polygon or not? So, we conceptually look into it. If we look at the same polygon, the same scan line, and there are 4 intersections, and you can see here, if you pick up a point somewhere in between inside the polygon between first 2 intersections, let us take intersection 1, 2, 3 and 4. There are 4 intersections in this particular scan line, correct? Now, take a point which is between the first and the second intersection, that is within a pair. Let us say this point is here somewhere. Now, if you know the xy coordinates of that point and keep looking towards left or towards right, you will find that the number of intersections of the polygon edges with this particular scan line is an odd number. If you look to the left, how many do you have on the left? That is 1. You have only one intersection to the left of the point the cursor is pointing to right now. Okay? When you look to the right, you have 1, 2 and 3. So, either you look left or right for this intersection which is at the middle, you have an odd number. The same is true for the second pair. If you take a point inside the polygon which is for this scan line which is lying within the second pair of intersections, then you will have the same. If you look to the left, you will have 1, 2 and 3. That means there are 3 intersections. To the right, you also have 1. So, it is basically an odd number. That means on a scan line, if you select a point within a polygon and count the number of intersections either to your left or right, you can pick up any direction, left or right, and if the count of the number of intersections is an odd number, the pixel is guaranteed to lie within the polygon. Again, there are a couple of exceptions, do not worry for the time being, that is the vertices, I know, but except vertices, we will see how to handle vertices anyway, but let us bother about only scan lines which are passing, not intersecting a vertex of a polygon. Otherwise, you can apply this criteria to check if a point is within a polygon by the following manner. I repeat again, okay, go to that particular point, keep looking to the left or right, not both, okay, only left or only right, and count the number of intersections in that direction. If that count is an odd number, then the point is within. If the count is even in any direction, it is outside the polygon. Let us see an example. With the same figure, if I take a point in that scan line which is between intersection number 2 and 3 somewhere in the background here on this scan line, and if you count the intersections to the left or right, the number of intersection is an even number. It is basically 2 on either side. So, the number of intersections to the left or right, if it is an even number, then the point is on the background or outside the polygon. If the count is an odd number, looking either left or either right, then the point is within the polygon. Remember this, even outside, odd inside, something like a binary decision as we did for an east and northeast pixel. We use this concept indirectly. Okay? So, look left or right and count the number of intersection points of the scan line with the edges of the polygon. So, find out the intersection points of this scan line with the edges of the polygon. Once you do that, then you count towards the left or the right the number of intersection points. And the condition which we have just described is very simple. If the number is odd, the point is inside, else it is outside the polygon. Correct? That is very simple. If the number is odd, the point is inside, otherwise it is outside the polygon. Now, the special case, we have to deal with vertices. This is the most interesting part of the scanline algorithm. Of course, there is other small mathematics involved in incrementing the intersection from one scanline to the other, but that is within a loop. But before you start the loop, actually you have to take care of the vertices problem, otherwise you might land up with odd number of intersection points. We will see when in some cases where the scanline is passing through a vertex, you may land up with even number of, usually it is even, but if it is passing through a vertex, in some cases you will end up with you will find that the number of intersections is an odd number, then you can't form pairs of intersection. Remember, you have to find out pairs of intersection and fill within pairs, and this concept works because of that inside outside test of a polygon, odd and even. Okay? So, that is the basic idea, that odd and even test of the count helps you to form pairs of intersection and fill within pairs, and that is how the fill polygon works. But there are other works to be done. One is of course updating the scanline intersections incrementally by an integer based on Bresenham's criteria. But till before that, before entering the for loop itself, you must take care of the vertices in such a manner that at each scanline you always get even number of intersections. And at each scanline, as long as you are getting somehow, if we can make, even if the line is passing through a vertex, if we somehow ensure that the number of intersection points are even instead of being odd, you can always form pairs and always fill, and it always works. So we will find that there are two different cases of scanline passing through a vertex of a polygon, and we will see with the case 1. That is a typical example which shows that the scanline is passing through a vertex of the polygon. And as I was talking before, what happens is the number of intersections of the scanline with the number of edges is showing as 3. But if you carefully look at this number 3, the center intersection point is the vertex where there are two edges of the polygon which are missing, I mean sorry, intersecting or meeting or intersecting, and hence this count of the number of intersections at this point should be basically conceptually be 2. So, if the central count is 2 plus 1 makes it 4, actually you are having 4 intersection points, but it shows 3. Okay? And it happens in this particular case when the scan line is passing through the vertex every time. You take the top scan line, as I was talking about a little bit earlier, that it will show only one intersection point, because that's again is a vertex and it's a meeting point of two different edges, and hence we have 1, but basically it should be 2. Similarly, you should have 1, 2 and 3 here, and then a 4, and if you can do that somehow, then what you have is you have 2 pairs of intersection and you can fill. Do not worry about what is done at that vertex, but right now visualize that the number is 3, but it actually should be 4. So, that is case 1. Okay. So, in this case basically we just put a note here that in such a case of this type of a vertex, we should add one more intersection to this type of a vertex where the scan line is passing through and make the number of intersections up from 3 to 4. Just increment the number of intersections from 3, you can see 3 intersections, but if we consider 2 only at the center, the number of intersections should be 4. So, that I hope the idea is clear. This is the first case of a scan line passing through a vertex. Let us look at the second case. Well, this is, I have to take a different polygon to illustrate a slightly different concept for intersection of a vertex with a polygon, and what we will see here is the first scan line, which shows that there are 1, 2, 3, 4 and 5. There are basically 5 intersections, and this concept is the same as the case 1. The concept is same in some cases as case 1, where you add just 1, you increment the number of intersections and make the number of intersections from 5 to 6. In this case, if you make from 5 to 6, what happens? Let us sequentially look at the numbering: 1, 2, 3, 4 and 5. So, that is an odd number, you can't form pairs. If you put the number of intersections at this point as 2, then you can have 1 and 2 as one pair, a 3 and a 4 as another pair, and a 5 and a 6 as another pair. So, you have 3 pairs you can form. You basically have the number of intersections as 6, which is an even number, and you can form hence 3 pairs of intersections. And as long as you have 3 pairs of intersections, you can fill in 3 different parts of this scan line from 1 to 2, 3 to 4 and then 5 to 6. Done. So, that is the adding one more intersection works here. Look at this particular case. This is very, very interesting. The second scan line, you see the number of intersections is 1, 2, 3 and 4. It is anyway an even number. What is the problem? Because only when you have an odd number, you should start worrying. You have an even number, so you can form 2 pairs and fill. There should not be any problem of the second scan line. But why is it drawn? You can easily guess that one of the intersection points is a vertex. One of the intersection points is a vertex of a polygon, but still the number of intersection points is an even number. Very, very interesting, isn't it? So, you have 1, 2, 3 and 4 even number of intersection, you can form 2 pairs, but the vertex is an intersection point. Intersection point is a vertex of the scan line. And if you apply the same logic as we have done in the previous 2 cases and add one more intersection point, from 4 you will end up with 5 intersections. Then you have an odd number. You can't add 1, 2 and 3 here, 4 and 5. You will have odd numbers of intersections. This is a very peculiar case where the we just said that the number of intersections should be an even number in general. When you are passing through a vertex, you have the number of intersections being odd. So, you increment and make it even and form pairs, that is fine. But this is the third case we are seeing, a very, very special case where the scan line is passing through a vertex, all right, but the number of intersections is even though it is passing through a vertex, we have an even number of intersections. And now if you follow the previous logic that whenever you find a vertex, please add an intersection, you are making the number of intersections from even to odd, and then you cannot run the algorithm because you cannot form pairs out of an odd number of intersections. So you have to do a special arrangement here to keep the number of intersections even as an even number in this case, even though it must be an even number, even though the scan line is passing through a vertex. So come back to this figure. As I was saying, there are 1, 2, 3 and 4, keep the even number. So this is a special case where we do not have to add the intersection. You keep the number 4 here as the number of intersections. Keep 4 means you don't add 1 and make 4 to 5 as you have done here by adding 1 and making 5 as 6 intersections for the top scan line. For the bottom scan line, you have to keep the number of intersections as 4. But how this is possible? Because if you put forward a theory and a programming step inside an algorithm that the algorithm step inside a program basically which says that whenever you find a vertex or a scan line passing through the vertex, just add one more intersection. That will make your odd number even. But if the total number of intersection itself is even, you can't add to make it an odd number. So you have to keep the number of intersections even, and that's a tricky part in the algorithm which we will see next in the remaining part of the lecture today. How to do this? How you do not need to add an intersection point here, but in this case you need to add an intersection point. You can already see from the figure that the vertices are two different types. This is what we will exploit to find out that if this is the type of the vertex, we add. If this is the type of vertex, we don't add. Add means add an intersection point to the scan line. Okay. So how do you quantify this, that this is one type of a vertex and this is the second type of vertex? This is what we are going to study next. So what is the difference between the intersection of the scan lines y and y prime with the vertices which we have been discussing now? I label the two scan lines as y and y prime, and we know from the previous figure, this is the same figure, only the vertices have been labeled with a slightly different color wherever the scan line is intersecting, that is number 1, and the two scan lines have been labeled y and y prime. We know that the intersection of y scan line y with the vertex needs to increment the intersection by 1, such that out of 5 intersections or from 5 intersections we have 6, whereas in the case of the scan line y prime, where it intersects the vertex in this red color dot, we don't need to add an intersection point and we need to keep the number of intersection points as 4. So it means for the scan line y, for y means scan line y, the edges at the vertex are on the same side of the scan line. We are trying to distinguish the vertex here of scan line y and the other vertex with the scan line y prime intersects. Remember, all the other blue dots are intersection points of the scan lines with the edges of the polygon. These are not vertices anymore. None of them, these blue dots, is a vertex of the polygon. Okay, so these are edges, intersection of clean edges with the scan line. The two non-blue dots, one is about purple in color and red ones, are the two intersection points which are vertices of the polygon, and the intersection point of the scan line with the vertex is what is giving us the problem. So if you look at this vertex of scan line y, which intersects at this point in the purple color, top scan line y, you will find that the adjacent edges which forms this vertex or meets at this vertex, they are on the same side. Same side means either top or bottom. In this case, they are on the top side of scan line y. It could be at the bottom as well, but they are on the same side. So that line which says that for y the edges at the vertex, that means there are two edges which is meeting that vertex. We are bothered about only those edges, and those edges at the vertex are on the same side of the scan line. Since they are on the same side of the scan line, this will need, for the time being, just note down or visualize that you need to add an intersection point if the edges are on the same side. Whereas for y prime, the edges are on either or both sides of the vertex. One is on the top and another is the bottom. If you take the scan line y prime and see the intersection of this red marked by red dot of this vertex of the polygon with y prime, the two edges which meet to form this vertex, okay, this particular vertex which is through which the y prime scan line is passing through, the two edges which meet to form this vertex are on two different sides of y prime. One is on the top, one is at the bottom. Okay. Whereas from scan line y, both the edges are were on the top, they were on the same side, means on the top, but it could be at the bottom also. So, bottom or top is the case is the same, but this is a different case where we will say that the edges are on both sides of the vertex. And in this particular case, when edges are on either side or both sides of the vertex, we require some additional processing to ensure that we don't increment the number of intersections. So, I hope it is clear. We are talking about intersection of scan lines with vertices, and whenever there is a case that the two edges which meet to form the vertex, so there are two edges which meet and form the vertex and the scan line is passing through that vertex. So, if the two edges are on the same side, on the top, or it could be at the bottom, the two edges could be at the bottom or on the top of the scan line, then you increment the intersection and make that intersection point, visualize that intersection to be of intersection of two edges with the scan line. So, just increment the number of intersections, that will make the number of intersection an even number from odd, and you can form pairs and fill. That is not a problem. In the case of the second line y prime, we had a scan line, and then of course, there was an edge coming meeting the scan line and going down. So, there was a vertex and a scan line came. I should come from this side and go down. It does not come and go up. The polygon vertex is such that the edge does not come and go up, it traverses through the scan line and goes down, possible. Okay. In that case, we do not add. You have to do something where you keep that intersection only as one, not in the previous case where we increment and visualize it or consider it to be two intersections in the previous case for scan line y, but in y prime we take that intersection as one only. So, I go back to this particular figure. So, for this intersection for scan line y, I must consider this to be two intersections, whereas for this particular red color intersection for scan line y prime, I must consider it as only one intersection. How to do this additional processing such that I can stop considering making my algorithm consider this to be one intersection and this to be two intersections. Vertex counting in a scan line, that is what we are bothered. Let us take, just to elaborate once again, I have labeled the vertices A, B, C, D and E, let us say. So, there are 5 vertices. In fact, the scan line y passes through point B which is a vertex, and scan line y prime passes through point D which is another vertex of the polygon. If that is so, to find out whether the edges are on the same side or on both sides of the polygon, you traverse along the polygon boundary clockwise or counterclockwise. Clockwise or you can be consistent, you have to be consistent. You either move in a clockwise type of arrangement or you can move in an anti-clockwise arrangement, there is absolutely no problem. Okay? But you must be considered, you can't move clockwise half of the algorithm and then go back. Okay? You can trace the polygon boundary either anti-clockwise or you can go clockwise as well. So, follow that. So, traverse along the polygon boundary clockwise or counterclockwise. The typical example of clockwise could be in this case A, B, C, D, E and so on, that is clockwise. Okay. Anti-clockwise could be other way where it is E, D, C, B, A and so on. So, these of course, I have labeled only 5 vertices out of about 8. About 9 vertices exist in this polygon, and I have labeled only 5 which are necessary for my vertex processing. So, that I hope this concept is clear, that what you mean by traverse along the polygon boundary clockwise and anti-clockwise. You have to do this before the iteration starts for each scan line. You have to do this what I will call as a pre-processing step or stage before the iteration for each scan line starts. You traverse along that and observe. What do you observe? Observe the relative change in y value of the edges on either side of the vertex. That is, as you move from one edge to another, from edge AB to BC, you find out what is the relative change in the y value with respect to B. With respect to B, these vertex are A and C on one side or not. So, you can have a look, you actually have to look into the vertices only and find out if A and C, the relative change, that means A minus B, if it is positive, C minus B also should be positive. So, that is another way of looking at it. So, you look at that change, and if that change is on one side, then of course you add an intersection, whereas when you are traveling from C to D to E, you see that the change is unidirectional. That means you are coming down in y coordinate from C to D, and then the y coordinate also keeps going down from D to E further. So, that is one type of a change where you do not need to increment, and in the case of B, A to B and back to C, the y coordinate has fallen down and then gone up. Okay. So, that is how you find out whether the edges AB and BC with respect to the vertex V are on one side of the scan line, or for the scan line y prime, the edges CD and DE are on two different sides of the scan line. Okay. So, you basically have to compare the y coordinates of the three vertices A, B, C to test for vertex B, and for vertex B compare the y coordinates of vertex C, D and E. When you compare these vertices, y coordinates of the vertices, you can easily find out whether the edges or the vertices themselves are on the same side of the polygon. Both could be on the top, both could be at the bottom, or each one is on the other side. Okay. That means the two vertices are on respectively opposite sides with respect to the scan line, and this is what you have to observe, the relative change in y value. Okay. So, vertex counting in a scan line, that is we continue with the same figure to discuss this. Check the condition that if endpoint y values of two consecutive edges monotonically increase or decrease, okay, then you count the middle vertex as a single intersection point for the scan line passing through it. This is the condition which is true for intersection or vertex D with scan line y prime. Scan line y prime is passing through vertex D, and what do? You check the endpoint y values of two consecutive edges. That means you look into the y value of vertex C, you look into the y value of vertex D, you look into the y value of vertex E. What will you find? For these two consecutive edges, the endpoint y values will be monotonically decreasing if you are traveling from C to D to A for clockwise traversal along the polygon, which we talked about, or even if you do counterclockwise, that means you are traveling from E to D and then to C, you will find that the endpoint y values for these two consecutive edges are monotonically increasing from E to D and then to C. I am assuming that the origin is the left bottom corner of the screen and y value is increasing upwards, x value is increasing to the right. So, that is what is my assumption, and if you do that, when you travel from E to D to C, the y values will increase monotonically, or if you travel clockwise from C to D to E, the values will decrease monotonically. So, if that is so, then you count the middle vertex D as a single intersection point and not two, and for the corresponding scan line y prime, and that is enough for you to show that you have even number of scan lines. So, for D you count it as one intersection and you have even number of intersections for that scan line y prime, and you can form pairs. Once you have an even number, you can form pairs. This condition of monotonically increasing or decreasing y values, remember the term monotonically increasing or decreasing y values will not be true for vertex B, because as you check the y coordinates from vertex A to vertex B to vertex C, the values will go down and then go up if you are moving in the clockwise sense. If you are moving counterclockwise from C to B to A, the value will decrease and then increase again. So, this condition of endpoint y values monotonically increasing or decreasing will not be satisfied for the vertex B for scan line y, it will only satisfy for the vertex intersection D for scan line y prime. So, hence I keep and I say that when this condition is satisfied for vertex D, I consider only one intersection, whereas for vertex B, since my condition is not satisfied, I increase the number of intersections by 1, and hence odd number of intersections for scan line y becomes an even number. Basically from about 5, exactly 5, you go to 6, whereas for scan line y prime the number of intersections remain exactly at 4, because we are not incrementing. Else the shared vertex, that is this first condition was for D, and it violates for vertex B, then the shared vertex represents what we call as a local maxima or minimum. There is a term called extremum which could be also used. It is a local extrema which we will use now and often used in literature, and we have a local minimum or a maximum on the polygon boundary, and we increment the intersection count, and this second paragraph is true for B vertex. The first paragraph holds condition holds good for vertex D, and the else condition means the top condition for monotonically increasing or decreasing does not satisfy. It does not satisfy for vertex B, it only satisfy, I repeat, for vertex D. So, on D I do not increment, for B I increment the number of intersections by one more. So, instead of 5 I have now 6, I can form 3 pairs, I can fill. In the second case for one line, Scanline Y prime, I have anyway 4 intersections, I keep 4 intersections because I am not incrementing, and when I have 4 intersections, I can form 2 pairs and I fill within pairs to obtain the region to be filled in within the polygon for Scanline Y and Y prime respectively. I hope the idea is getting clear. So, if a vertex is a local extrema, this is an example of 2 edges meeting at a vertex on one particular side, and both on one side. In fact, it is below the scan line. The previous, some of the examples had been on the top, both or some of them have been on the bottom. So, if the vertex is a local extrema, that means you either have a maximum or minimum at that point, something like a peak. Consider or add 2 intersections for the scan line corresponding to such a shared vertex. So, if a shared vertex is a local extrema, which basically means the condition that both the edges are on the same side of the scan line, then we increment by 1 and or consider that vertex to be 2 intersections. But however, you must avoid this case when such a thing happens, that the shared vertex is not a local extrema. That means the edges, whether you are traveling counterclockwise or clockwise, shows that they are on either side of the polygon. In this figure, there are basically 3 scan lines, and you are now at scan line number I, and the scan line I plus 1 is shown in dashed 1. There is a vertex intersection, and this is the case of a vertex where you should not add an intersection and consider it to be only one intersection point. So, you must avoid this case to add an intersection. If you add, you will have a problem because you will change the number of intersection points from even to an odd number. So, you must not add in the second case. In the first case of a local extrema, you have to add. To implement the above, the following thing is done. While processing non-horizontal edges, generally, because you do not process horizontal edges, we will see why it is not necessary later on. So, while processing non-horizontal edges along a polygon boundary in any order, check to determine the condition of monotonically changing, that means increasing or decreasing endpoint y values. So, you try to observe while processing the edges and keep checking at the vertex for these monotonically changing values of endpoint y values, and if you do so, then what you is basically the algorithm says is you treat this vertex in such a manner that you reduce one of the edges by one particular scan line. So, if this is the vertex before processing where 2 edges were intersecting, what you do after processing is reduce this edge by 1 unit in length and allow the edge to only stop here, not go up to this point, and that is sufficient to provide you that this point is not a vertex, but is the endpoint of one edge of a polygon, and you will intersect the scan line only with one edge, but with not the other. This is the sort of processing which could be done. This is another scenario, either you are traveling counterclockwise, clockwise, or whatever the case may be. When you find such monotonically changing values where the edges are on both sides, you reduce this the edge of the edge for processing. Okay. So, after processing, you reduce the edge. When you are going from top to bottom, bottom top does not matter, you reduce on one side the edge, and that will show that the scan line has only one intersection point. Okay. So, it basically says that shorten the lower edge to ensure that you have only one intersection point at the vertex. Okay. So, before processing, you had both the edges meeting at this point. When you shorten one of the edges after processing, then you have only at this vertex only one edge coming, the other edge does not reach the vertex, and henceforth you will land up with only one intersection point and not 2. That is what you do. So, we will wind up this class and continue with the remaining order where we revisit the Scanline PolyFill algorithm. In brief, if we visit it, intersect scanline with polygon edges, fill between pairs of intersections, and that is the basic structure. From y min to y max, that is from scanline top to bottom, intersect scanline with each edge, short intersections by increasing s, and fill pairwise. Okay? So, these are the three important steps once of the basic structure of the scanline filling algorithm, but there is a lot of overhead to handle the vertices. Okay? So, while you actually intersect scanline with polygon edges, fill between pairs, that is the basic idea or the basic structure of the algorithm, but what you basically need to do is do a lot of pre-processing. Do a lot of pre-processing prior to this, such that you can handle this vertex problem inside the loop. Inside the loop, I just want you to, the algorithm says that you just keep on incrementing the scanline from one to another, from either top to bottom or bottom to top, whatever the case may be, and if the vertex problem has been handled a priori by shortening the edges as may be necessary for monotonically increasing or decreasing y values, if that is already been done. Okay? Then what it basically means is you have to just increment the scanline intersections and go from one scanline to another along an edge, reach vertices, come up with new edges and so on. That is how you basically implement, but there is a lot of pre-processing before. There is a lot of pre-processing which one has to do earlier in terms of vertex manipulation, such that this incremental scanline based algorithm can work smoothly, and it is guaranteed that at each scanline you get even number of intersections, form pairs and fill. So, we will wind up this class where we will start again from the next class at this point, where we revisit the Scanline PolyFill algorithm. In brief, the basic idea is intersect scanline with polygon edges and then fill between pairs of intersection, and the three steps is that from scanline y min to y max, you intersect scanline with each edge, sort intersections by increasing x, and fill pairwise. Actually, again I must repeat here, there is an overhead prior to this loop between scanlines, that is number one, and then within each loop you are not freshly calculating the intersections. You never do that. You always increment along an edge to get the next intersection point from the current one, and we use properties similar to Bressenham's algorithm midpoint criteria, similar to that, which are called edge coherence and scanline coherence. We will start with this basic structure and look into this concepts and simplified calculations to compute these intersection points very fast, and also look at algorithms which will handle the vertex problem. We know how to handle that vertex problem. We will see what data structure is used to store the polygon vertices and handle this problem of vertices by shortening edges, and then of course at each scan line from one to the other, how to increment the intersection points and get to the next scan line intersection points. Okay, that will be the main treatment for the next class for scanline fin algorithm. We have studied the concepts and the geometry behind it today, and we will move towards the algorithm in the next class. Thank you very much.